In this video, we'll talk through the lecture notes for section 4.1, which is called separation of variables. Separation of variables is an important technique that is used to solve partial differential equations on bounded domains by turning them into multiple ordinary differential equations. We already saw this method. In section 3.1, we used it to solve a particular equation, which was the heat equation, where the constant was equal to 1. This was the homogeneous problem, where the boundary conditions are 0. And that's important when you're using the method of separation of variables. So how does the method work? So assume that there is a solution of the form x times t. That is, we assume that we can write u as a product, a function of x times a function of t. Now I'm calling the function of x capital X and the function of t capital T, just so it's easy to distinguish which one is which. Of course, that means that we have x at x and t at t, but I'll try to be careful about which one's capital and which one's lowercase. So the idea is we start by assuming that you can write u as a function of x times a function of t. And you'll find that there are multiple solutions. We end up finding a sequence of solutions, one for each natural number n. So we call them u sub n is equal to capital X sub n at x times capital T sub n at t. This gives us a sequence of solutions, and then the general solution is going to be an arbitrary linear combination of this infinite number of solutions. U at x comma t is equal to the sum, n equals 1 to infinity, of c at n times capital X sub n times capital T sub n, where these cn's are arbitrary real numbers. This method can be applied to many partial differential equations on bounded domains that satisfy the following conditions. 1. The PDE is homogeneous. And 2. The boundary conditions are homogeneous. The PDE being homogeneous means that you don't have a source term here. The boundary conditions being homogeneous simply means that at the boundary you're holding it constant at 0. There are ways of dealing with situations when you have non-homogeneous boundary conditions or a non-homogeneous PDE. But for the time being, to introduce the method, we're going to assume homogeneity. If you have non-homogeneity, then you have to change it in some way, alter it, so that it becomes homogeneous if you want to use this method. Because really what we're using at this stage is the principle of superposition. And in order to have a solution, it's important that all of the individual solutions are solutions to the homogeneous problem. So in this section, we're going to apply the method of separation of variables to the heat equation and the wave equation. So let's begin by looking at the heat equation. So here we have the homogeneous heat equation. The first partial derivative of u with respect to t is equal to k times the second partial derivative of u with respect to x. Here we're looking at a bounded region, so x goes between 0 and L. We're also assuming homogeneity at the boundary, so u at 0 comma t is equal to 0 for all time t, and u at L comma t is equal to 0 for all time t. So that just means that at the boundary, when x is 0 and x is L, we're holding the temperature constant at 0. We also have an initial condition right here. U at x comma 0 is equal to f at x. That means the initial temperature at any point is given by some prescribed function x. And again, we're looking at a bounded region. X goes between 0 and L. Here, L is some positive number that represents, for example, the length of a bar. So we start by assuming that u is equal to the product of a function of x times a function of t. And as usual, I'll call those functions capital X and capital T, just to make it easy to distinguish which one is which. So if u is equal to capital X times capital T, then the partial derivative of u with respect to t is equal to capital X times capital T prime, because capital X has nothing to do with t. Similarly, the second partial derivative of u with respect to x is the second derivative of capital X times capital T. Because once again, there are no x's inside capital T, so we just treat that as a constant when we're differentiating with respect to x. The heat equation, u sub T equals k times u sub xx, this can now be restated in terms of capital X and capital T. So on the left we have capital X times capital T prime. That's the first derivative with respect to t. And on the right we have our constant k times the second derivative of capital X times capital T. So that is our heat equation. So now what we do is we separate the variables, which is why this method gets the name that it does. So we leave the t prime on one side, and we leave the x double prime on the other side. And then we want to get all of the t's on one side and all of the x's on the other side. So what we can do is first we divide both sides by t at t, and that puts that t at t down here. Next we can divide both sides by x at x, and that puts the x down here, the capital X down there. Why are we allowed to divide by these? Well, we're going to assume that they're not always equal to 0. If they're always equal to 0, then u is the trivial solution. And that's something that we want to avoid, assuming, of course, that f is not equal to 0. At any rate, what we're trying to do is we're trying to find non-trivial solutions. So we can assume that x is not always equal to 0 and t is not always equal to 0. That is capital X and capital T. It's also traditional to divide by the constant and put 1 over x on the left side with the t prime over t. So now we have an equation where on the left side we have a function of t, and on the right side we have a function of x. That means that each side must be constant. So on the left we have a function of t, and we're saying that that's equal to a function of x. The only way a function of t can be equal to a function of x is if both of those functions are constant. You can think about it this way. Imagine holding t constant on the left, but allowing x to vary. If this ratio is always equal to the quantity on the left, but you're holding t constant, that means regardless of the choice of x, it must be equal to the same constant. Similarly, if you imagine fixing a value for x, then the quantity on the right is constant. And then if you allow t to vary, then regardless of the choice of t, you'll always end up with the same ratio. So that tells us that these ratios must be constant, and so there must be some constant lambda such that this ratio is equal, well, we don't say lambda, we say equal to negative lambda. That doesn't mean necessarily that lambda is positive or that minus lambda is negative. It's really just for convenience, as you'll see. This minus lambda is what is known as the separation constant. We know that these ratios, the one on the left and the one on the right, are constant, so we can give them some value. So let's call it minus lambda. That's called the separation constant. This leads us to two separate ODEs. Again, that's the name of the method, separation of variables. Now, you have separated the problem into a second-order differential equation in terms of x and a first-order ordinary differential equation in terms of t. But these are both ordinary differential equations, not partial. So we can get x out of the denominator now and t out of the denominator, and we can write the one on the left as capital X double prime plus lambda times capital X is equal to 0. And on the right, we have capital T prime plus lambda times k times capital T is equal to 0. So that's what you get if you just multiply this kt over to the other side and then add everything. You'll have t prime plus lambda k times t. So this gives us two ordinary differential equations. The one in terms of capital X, that's a second order, and the one in terms of capital T, that's a first order. Now our boundary conditions also give us some information. we're assuming that they're homogeneous, so u at 0, comma t is equal to 0, and u at L, comma t is equal to 0. So u is equal to capital X times capital T. So this first boundary condition, u at 0, comma t equals 0, translates to x at 0 times t at t is equal to 0. And also, u at L, comma t equals 0. That gives us x at L times x at t is equal to 0. Now, again, we're assuming that u is non-trivial, so that means that u is not 0 all the time. So these conditions actually tell us something about, these boundary conditions actually tell us about boundary conditions for x. So this first condition, x at 0 times t at t is equal to 0. Either x is 0, or if it's not, then capital T is always equal to 0. But if capital T is always equal to 0, then in this original assumption that we made, where u could be written as capital X times capital T, if capital T was always 0, then u would always be 0 and it would be trivial. And we're assuming that u is not trivial. So that means capital T at t isn't always 0. So that means x at 0 must be 0, which is what we have here. Similarly, if you assume that u at L, comma t is equal to 0, then capital X at L times capital T at t is equal to 0. But again, we don't want capital T at t to be constantly equal to 0. So that means x at L is equal to 0. So we now have boundary conditions on x. This is really why we want homogeneity in the boundary conditions, because that actually tells us definitely something about x at the endpoints, at the boundary. We now have a boundary value problem in terms of x. Capital X double prime plus lambda x equals 0, with boundary conditions x at 0 is 0 and x at L is x at L is also 0. We already saw in one of the previous lecture videos that this has non-trivial solution only when lambda is positive, so I'll omit those details when lambda is 0 or a negative number. But we found in those cases that the only solutions were trivial. So in case that lambda is positive, the characteristic equation is r squared plus lambda equals 0, which has solutions r equals plus or minus lambda. So this tells us what the general solution is for capital X. Capital X at x is some arbitrary constant a times cosine of the square root of lambda x plus some arbitrary constant b times sine of square root of lambda x. So this is the general solution. We use the boundary values to figure out what a and b might be. So x at 0 is a times cosine of 0. Cosine of 0 is 1, plus b times sine of 0. Sine of 0 is 0, of course. So that tells us that a is equal to 0. A times 1 is a plus b times 0. So a is equal to 0. So there's one figured out. Well, what about at the other boundary? X at L is equal to, well, we know that a is 0, so let's just get rid of that altogether. So it's just going to be b times sine of the square root of lambda times x. But now we're evaluating at x equals capital L. So we have b times sine of the square root of lambda times L, and that's equal to 0. This doesn't tell us what b is, but it does tell us that this product has to be equal to 0. Now, we don't want b to be equal to 0 because we already showed that a was 0. If b was 0, then capital X is constantly 0, which is something we've been trying to avoid because that will give us trivial solutions. So what that means is that sine of square root of lambda times L must be 0. So that means we're looking for values where sine gives you something which is 0. And of course, sine is 0. Sine of theta is equal to 0 when theta is equal to n times pi for any integer n. Now, in this case, we're looking at lambda that's positive, so we're just going to assume that n is a positive integer. So in this case, n is a natural number. Okay, so that tells us that what theta is, but theta is this number right here. So theta is square root of lambda times L. So that means we want the square root of lambda times L to be equal to n times pi. So in other words, if you solve for the square root of lambda, you're going to get this expression here. The square root of lambda is equal to pi n over L. So what does that tell you about lambda? Well, you square it, and you get lambda is equal to the square of the quantity pi n over L. So there is a solution for each n in the set of natural numbers. So we have a lambda sub n for each n, which is pi n over L quantity squared, and that corresponds to an x sub n, which you obtain by simply plugging in that lambda n into this expression here, or rather here. We've already established that a was equal to 0, so this term goes away. So we're looking at x is equal to capital B times sine of the square root of lambda x. But now we know what lambda is. We have a different lambda for each n. We're calling it lambda sub n. So if you plug that lambda sub n right into there, then you end up with the square root of lambda sub n, which is pi n over L. So x is going to be some arbitrary constant times sine of pi n over L times x, which is what we have here. Now we've omitted the constant b for now. Later on we're going to insert some arbitrary constants, and that will take care of the arbitrary constant b. We're going to have a different arbitrary constant for each n, so the constant would be b sub n. But we'll see that in a moment. So we have terms for these. We call lambda n an eigenvalue and xn the corresponding eigenfunction. That's really because of this equation here. So we have this capital X prime prime plus lambda x equals 0. Or we can write that as minus x prime prime is equal to lambda x. So on the left here we have a differential operator. So the idea is we're looking at the opposite of the second derivative of x with respect to x, and this is evaluating capital X. This is equal to lambda x. So this thing that we have on the left here, minus the second derivative with respect to x, this is a differential operator, and it's acting on x, and it's giving us back a lambda times x, capital X in this case. So the differential operator is the second derivative with respect to lowercase x, the variable x, and it's acting on this capital X. And it gives us back lambda times capital X again. So that's why we call lambda an eigenvalue, because it's an eigenvalue for this differential operator. And the corresponding capital X is the eigenfunction, is what we call it. I can just do that to make them look more like capital X's. Just give them some serifs, I guess, like so. There we are. So that's why we call lambda n an eigenvalue and xn an eigenfunction. And we'll talk a little bit more about this in the next section. So what we've done is we've solved our first ODE, which was the ODE in terms of capital X, x double prime plus lambda x equals 0. So we solved that and we found a sequence of such functions. The next thing to do is to solve for t in our second ODE. So the second ordinary differential equation will now depend on lambda n. We know that lambda has to be one of these lambda n values. So here's our equation. T prime plus k lambda nt is equal to 0. Now this is just a first order differential equation. So we can actually use separation of variables in the first order, or in the ordinary differential equation sense. So this is t prime equals minus k lambda nt. Get all of the t's on one side. then you integrate, you get the natural logarithm of the absolute value of t is equal to minus k times lambda n times t plus some constant of integration. So this is some lowercase c. This is a lowercase c which will only be with us temporarily, because then we exponentiate both sides. So you get capital T is equal to plus or minus the exponential of what's on the right, e to the minus k lambda nt plus c. But that c is a constant, so we can write this as, we can factor it, so to speak, and then we can write this as e to the c times e to the minus k lambda nt. And we can put the plus or minus in there, and we just call this one capital C or uppercase C. And this one will also only be with us for just a moment, because what we have now is we have that t is equal to some constant times, that's supposed to be a c, some constant times e to the minus k lambda n t. Let me just fix my lambda n there. Lambda n t. Okay. So this is our solution, and notice again it depends on n. So this t will depend on n. So I've just rewritten it here. We omit the c for the same reason that we omit this b. This b over here. We omitted that b, and for the same reasons we're going to omit this c. We'll see the constants in just a moment. So what have we discovered? For each n in the set of natural numbers, we have a solution u sub n to the heat equation that satisfies the boundary conditions. So the solution to the boundary value problem that we have obtained is u at, that's not what I meant to select, u sub n at x comma t is equal to the product of a function of t times a function of x. Okay, so that's supposed to be x sub n, of course. So for each n, we have a u sub n, which is the product of capital T sub n times capital X sub n. And so we know what these are. T sub n is this exponential, e to the minus k lambda squared n squared over L squared times t. And X sub n is the sine term, sine of n pi x over L. So that gives us a solution to the differential equation that satisfies the homogeneous boundary conditions. However, it doesn't satisfy the initial condition. So you might remember, if we scroll all the way back, we did have an initial condition. It's all the way up here. Right here, we had an initial condition. U at x comma 0 is equal to some prescribed function f at x. Now, if we go back down to our solutions u sub n, there's no reason to assume that this will satisfy our initial condition. But what we really want is not just the u sub n individually, we want to take a linear combination of those. So we add them all together. So this is why we omitted the constants before. So we have this constant b sub n. So this is a linear combination. This is, for the time being, an arbitrary linear combination of all of these u sub n solutions. So each one of these, this is u sub n at x comma t. So we're looking at the sum n equals 1 to infinity b sub n u sub n x comma t, where this b sub n is an arbitrary constant. Now we can think of this arbitrary constant in terms of our other constants. So b sub n would be this is our capital B times our capital C. Now of course each one of these depends on n. So if we go back to the previous slide, since each one of these solutions depended on n, this should really be b sub n. And this should be c sub n. I didn't really call them that because we just omitted them immediately anyway. So that can be a lowercase c sub n as well. C sub n. I mean, there's no point in me even putting these here because we're not going to be using them. But the idea is that they all depend on n. So what we could do is we could just keep them around and then just just group them together and call their product lowercase b sub n. However you want to look at it, b sub n is a constant. And it's an arbitrary constant because capital B and capital C were arbitrary constants. But even if we didn't have them, what we're doing is we're looking at an arbitrary linear combination, and that gives us what we can call the general solution. Now we want this to satisfy the initial condition, u at x0 is equal to f at x. So what that means is, well, let's evaluate, let's look at this general solution when t is equal to 0. So we're leaving x alone, and we're looking at t equals 0. So u at x comma 0. So if you look at our general solution, when t is equal to 0, the only t is right there. So this is the only t. So we want that t to be equal to 0. So all of this becomes 0. So it's e to the 0, which is 1. So that term just becomes 1. So what are we left with? We're left with b sub n, which is that b sub n, times the sine term, sine of n pi x over L. There are no t's here, so that doesn't change. This is our u at x comma 0. It's equal to the sum, n equals 1 to infinity, of bn times sine of n pi x over L. And we're going to say that this, if it satisfies our initial condition, must be equal to f at x. But then you stare at that and you go, oh wait, this means that f is equal to a sine series. So it follows that f must be representable as the sine series, and in fact it's this sine series. So f at x is this sine series, so that means if you want to know what the bn's are, you just need the coefficients of your sine series. And as it happens, we have a formula for that. If f is representable as a sine series, let me just highlight these. So if f is representable as a sine series, then its coefficients are given by this formula, 2 over L times the integral from 0 to L of f at x times sine of n pi x over L dx. That gives us bn. That gives us bn, which is this bn. So if you know that f is a sine series, we have a formula for computing its coefficients, and there it is. So that tells us that the solution to the homogeneous initial boundary value problem is what we have here. U at x comma t is equal to the sum n equals 1 to infinity of bn times e to the minus k pi squared n squared t over L squared times sine of n pi x over L, where the bn's are no longer arbitrary coefficients. In order to satisfy the initial condition, they must satisfy this formula, or they're given by this formula, rather. So this bn is equal to that bn, and those bn's are computed in this way. So that uniquely determines the bn's. Now, on a side note, we can actually plug the formula for bn back into u at x comma t directly. You have to be a little bit careful if you do that. So there is an x here in the formula for bn. bn is equal to 2 over L times the integral from 0 to L of f at x sine of n pi x over L dx. But notice x is just a dummy variable here. We're just integrating with respect to x. X actually serves a purpose. It's an argument for u. It's one of our input values. It's our variable. So if you want to plug this formula for bn back into the formula for u, you have to change your variable of integration. So we can just change it to c, for example. So now we have bn is equal to 2 over L times the integral from 0 to L of f at c times sine of n pi c over L dc. So it's just a dummy variable that we're using as a variable of integration. Now we can take that and plug that back into, we can take this value for bn and plug it back into here if we want. And if we do that, we get something kind of interesting. We get that u at x comma t is equal to the sum, n equals 1 to infinity, of these bn terms. Okay, so suppose that we integrate term by term. Basically what that means is we take the integral out. Then notice that we're going to have some very complicated function times the initial condition. So we just call this complicated function here, we call it g. So it depends on several things. It depends on x, so you can see an x dependency right here. It depends on xi. That's from our variable of integration. And it also depends on t, which is right here. So it depends on x, xi, and t. So we just call that g evaluated at x, xi, at t, and we can see that our function u can be written as an integral. But it's not just any integral, it's the integral from 0 to L of this g function times f, where f was our initial condition. So we can think of u as being given as an integral operator on the initial condition. The idea being that you start with a certain condition, your initial condition f, and it changes over time. And how does it change? Well, it's determined by g. You're integrating by g. It's given by this integral operator. So we can write the solution as an integral. We call this the Green's function, this g at x, c, comma t. This function g, we call it the Green's function for the problem. And we've encountered something like this before when we were talking about solutions to the heat equation, and we ended up with the heat kernel. And that was also a Green's function for a problem. So we've encountered this idea before. So let's look at an example now. So let's solve the initial boundary value problem u sub t equals 4 times u sub xx. So this is the heat equation with constant k equals 4. Now in this particular problem we're going to choose our boundary so that L is equal to pi. So that's our L. So we have our heat equation on this bounded domain where x goes from 0 to pi, and t is, of course, represents time, so that's a positive number. Our boundary conditions are going to be homogeneous, so u comma 0t, or I think what I meant to say was u at 0 comma t is equal to 0, and u at pi comma t is equal to 0. So we just mean that at the boundary the temperature is being held constant. Our initial condition, u at x comma 0, is going to be given by this combination of signs, 2 times sine x plus 5 times sine of 3x. Now, what you might notice is that this is a sine series. We already have a sine series here. That will definitely come into play later. So the solution to the initial boundary value problem is just the formula that we've already established. You just plug in all of the appropriate values. U at x comma t is the sum, n equals 1 to infinity, bn times e to the minus 4n squared pi t over pi. So there should be a pi in the exponent, but there's also an L. So you have a k n squared pi squared t over L squared. Now in this particular case, k is equal to 4 and L is equal to pi. And so this pi squared term cancels with that L squared term, and that's why you don't see them here. Now I guess I should put the minus sign in there, not that it matters for this discussion. But anyway, so the pi squared and the L squared cancel. Similarly here, this would be n pi x over L, and the pi and the L cancel again. So now we have that u at x comma t is equal to the sum, n equals 1 to infinity, of bn e to the minus 4n squared t times sine of nx. Now in order to determine the bn's, we need to find the Fourier coefficients for our initial condition. Now here it's important that we notice that our sine terms are sine of nx, and that's also true here. So this is sine of nx where n is equal to 1, and this is sine of nx where n is equal to 3. So we already have u written as a sine series, and we can actually just pick off the coefficients. We've got 2 and we've got 5. So the 2 corresponds to the case where n is equal to 1. So that tells us that b1 is equal to 2. The 5 corresponds to n equals 3, so b3 is equal to 5. Otherwise, all of those coefficients are equal to 0. So bn is equal to 0 unless n is equal to 1 or n is equal to 3. So what does that tell us? That tells us we just plug in bn equals 0 except for n equals 1 and n equals 3. When n is equal to 1, b1 is equal to 2. So b1 is equal to 2. That's this 2 right there, which comes from here. And when n is equal to 3, we have b3 is equal to 5, which is that 5 here. Now this only works because our argument here is n times x. It has to be the same as this argument here, n times x. If I had something like pi times x here and 3 times pi x here, then I wouldn't be able to just pick off the coefficients that way. Because it's not enough that it's a sine series, it has to be the right kind of sine series. It has to be the sine series over the right length of interval. In other words, it has to have the right period. So that's our first example. Let's look at another example. So here again we have the heat equation, this time k is equal to 9. So solve the initial boundary value problem. So in this case, L is equal to 3. So the length of our interval is 3. So if we imagine that this is a rod, then its length is 3, and we're holding the temperature constant at 0 at both endpoints. Now, for some reason, there's a pi here. That should not be the case. That should be a 3. The length of this interval is 3. Who knows where that, maybe that was a copy-paste error or something like that. All right, so the solution to the boundary value problem we've already determined. It's u at x comma t is equal to the sum n equals 1 to infinity bn e to the minus 9. This is k right there. Pi squared n squared times t divided by this 9. This is L squared. Now you know why I chose the interval to be length 3, so the constants would cancel. So we just end up with the sum, n equals 1 to infinity, of bn e to the minus pi squared n squared times t, and this is multiplied by sine of n pi x over 3. Again, this 3 here, this is the length L. Okay, so bn is the coefficients of the sine series. And the sine series is the sine series of our initial condition, which is right here. So this is what we were calling f at x. So we need to find the sine series of that. Notice that this is a step function. It's f if x is between 1 and 2, and it's 0 otherwise. Now remember that this is actually a length 3 interval. So 1, 2, 3. So that's the length of our interval, starting at 0, of course. And it's only 1 between 1 and 2, so it looks like this. But otherwise it's 0. So that means it's 0 between 0 and 1. It's 1 between 1 and 2, and then it's 0 between 2 and 3. So this is a unit pulse, or a square wave of height 1. So we want to find the Fourier series, the Fourier sine series for this. So we can integrate bn is equal to 2 over L. So this is 2 over L. So again, the denominator here, that's L, times the integral from 0 to L of our initial condition f at x. So this is f at x times sine of n pi x over L dx. So again, that 3 in the denominator, this is our L here. Okay, so we know that our initial condition is 0 outside of the interval 1 to 2, so we're just integrating from 1 to 2. So it's 2/3 times the integral from 1 to 2 of sine of n pi x over 3, because the function is just 1 when it's not 0. Now this is easy enough to integrate. This is 2/3 times minus 3 over n pi cosine n pi x over 3. The antiderivative of sine is negative cosine, of course, and then we just divide by the constant. So we divide by n pi over 3, which is where we get that 3 over n pi here. So you just divide by that constant. And we evaluate from x equals 1 to x equals 2. And if you do that, you should end up with, well, so the 3's cancel here, you can see, and so you have minus 2 over n pi times cosine of 2n pi over 3 minus cosine of 1 n pi over 3. So that gives us our coefficient. So this is our bn here. So u at x comma t is equal to this expression, where all of that's our bn. Those are just the coefficients of the Fourier sine series, bn. So it would be difficult to actually compute values of this for an arbitrary x comma t, but only a few terms of the series are needed for a good approximation because of how quickly this exponential term decays. It decays very quickly. So if you want to find a good approximation, you only need a few terms from this series. So that's our second example for the heat equation. We might revisit the heat equation before this lecture is over, but let's talk now about the wave equation. So we're going to look at the wave equation on a bounded domain. So consider the initial bounded value problem of a string of length L with fixed ends. So the wave equation is the second partial with respect to t is equal to some constant, which we're calling c squared, times the second partial derivative of u with respect to x. So that's our partial derivative. X goes from 0 to L. We're thinking of L as the length of a string. Now the endpoints are fixed, so we're imagining that they're fixed in a way so that there's zero displacement. So u at 0 comma t is equal to 0 and u at L comma t is equal to 0 for all time. So we're imagining that the string has fixed endpoints. So u measures the displacement, so the fixed endpoints will have zero displacement. So that's what the homogeneous boundary conditions mean. Now, we want homogeneous boundary conditions, but we are allowed to have non-zero initial condition. So we have u at x comma 0 is equal to f, some prescribed function f, and the derivative u sub t at x comma 0 is given by some prescribed function g. So this is the initial displacement and this is the initial velocity. So those are given by some prescribed functions f and g. So we're going to assume that a solution has the form u at x comma t is equal to a product of a function of x times a function of t, which again I'm going to call capital X and capital T. So then our partial differential equation becomes an ordinary differential equation. So on the left, our second partial derivative with respect to t, our function capital X doesn't depend on t, so it's just going to be capital X times the second derivative of capital T. And then on the right we have c squared, of course, and then we also have u at x, u sub xx, that is to say the second partial derivative of u with respect to x. But again, t has nothing to do, capital T has nothing to do with x, so it's just the second derivative of capital X with respect to x. So once again we separate the variables. So on the right we're going to have x double prime, and I'm just going to divide by capital X at x. So we're going to have this term x double prime divided by x. Now on the left we have, let me just get rid of some of these. On the left we have this t double prime, and we divide by capital T. Now I don't know why I didn't put a t at t there. So it should be capital T at lowercase t. Who knows why I neglected to include that. Now it's also traditional to get the constant c squared with the t's, so we're going to divide both sides of the equation by c squared. So that gives us two ratios. On the left we have a ratio that's entirely in terms of the variable t, and on the right we have a ratio that's entirely in terms of the variable x. So we have a function of t is equal to a function of x. The only way that can happen is if both of those are constant. So these ratios must be constant. So we'll just let them be equal to minus lambda, which again is our separation constant, just like before. So now we have two ODEs. We have first one in terms of capital X. we obtain that one in exactly the same way that we did before. So we look at x double prime over x is equal to minus lambda. You multiply by capital X and then just add. So you'll have lambda double prime is, or rather, capital X double prime plus lambda x is equal to 0. So that's where that one comes from. And then we have the same sort of thing over here. So this is 1 over c squared times t prime prime over t equals minus lambda. So you multiply by c squared times capital T, t prime prime equals minus lambda c squared t, and then you just add this minus lambda c squared t to the other side. So now you have another second order ordinary differential equation. So in the case of the heat equation, we had a second order and a first order. Now they're both second order. This isn't too surprising because we're dealing with a wave, a vibrating string, so it's not surprising that there's going to be lots of things that oscillate. And solutions to this type of second order ODE tend to be sines and cosines, so things that oscillate. So the boundary conditions are the same as before. So we end up just like we did before with x at 0 equals 0 and x at L equals 0. So we have the same boundary value problem here that we had the last time. X double prime plus lambda x equals 0, and it's also 0 at the boundary. So this is the same boundary value problem as before. Same boundary value problem as before. So we already solved this one. We found that there was a solution for every positive integer n, and we called our corresponding lambda, we called it lambda n. I should say, when I say a solution, I mean a non-trivial solution. So for each n, which is a natural number, we found that there would be a non-trivial solution provided that lambda was equal to this number right here. So we called it lambda sub n because it depends on n, and it's equal to n squared pi squared over L squared. And this we called our eigenvalue. And the corresponding eigenfunction is capital X sub n is equal to sine of n pi lowercase x over L. So that's exactly as before. The problem changes now, because now to solve for t, we don't have a first order differential equation, we have a second order differential equation. T double prime plus lambda c squared t. Now we know that lambda has to equal lambda sub n for one of these n's. So lambda sub n has to equal one of these. Okay, so that means we're going to put a lambda n there. That also means that t will depend on n. So we will see that t is actually equal to t sub n. It depends on n. So to solve this, we form the characteristic equation. R squared plus lambda n times c squared is equal to 0, where lambda n is equal to one of these eigenvalues here, n pi over L quantity squared. So that means that r is equal to plus or minus the square root of lambda n c squared. So that gives us plus or minus n pi c over L. So the general solution to the second order ODE is, again, it depends on n, so we're going to call it t sub n. So it's sum a sub n times cosine of n pi ct over L. So n pi c over L, that just comes from right there, plus bn times sine of n pi ct over L. Okay, so that gives us the general solution. We don't have boundary conditions for t, we have an initial condition, but we're probably not going to be able to determine the coefficients a sub n and b sub n just for this function using the initial condition. So we do what we did before. We form an arbitrary linear combination of the solutions u sub n. So u sub n is equal to x sub n times t sub n. So we just write that out here. So here we're doing what we talked about before. We're just going to group together our arbitrary constants rather. So a sub n, so this lowercase a sub n comes from our arbitrary combination. So we're taking an arbitrary linear combination. That's where these coefficients a sub n come from here. Capital A sub n and capital B sub n come from here and here. But now what I'm going to do is lowercase a sub n times capital A sub n I'm going to call c sub n. And lowercase a sub n times capital B sub n I'm going to call d sub n. So what that gives me is that u sub x comma t is equal to the sum n equals 1 to infinity of c sub n times this cosine term. Let me just get rid of some of these extra circles and whatnot. Okay, so u at x comma t is the sum n equals 1 to infinity of this c sub n. That's the product of these a sub n's. So it's going to be sine of n pi x over L times cosine of n pi c t over L. So here's the cosine term. This cosine term is right here. Okay. Now we have a b sub n term right here. And now b sub n times a sub n gives you d sub n. So that's this d sub n right there. And that's times sine n pi c t. Now there's also the sine term. There's also this sine term here. Now I'm actually not going to distribute it. I'm just going to put it at the end here. I'm going to leave it factored out. The idea here being that all of our functions of t are inside the brackets. All of our functions of t are here. And on the outside we have our function of x. Okay, so we want to identify Cn and Dn, and for that we use our initial conditions. So we're looking at u at x comma 0. So this is our first initial condition. U at x comma 0 is equal to f at x. So we just plug in t equals 0. Now if we do that, if t is equal to 0, then this cosine term becomes 1. T is equal to 0. So this is just cosine of 0 is 1. Now on the other hand, the sine term, if t is 0, this is sine of 0, which is 0, so all that goes away. So you're just left with Cn times cosine. So Cn times, well, cosine is 1 in that case. So let me just make a little remark here. So if t is equal to 0, then cosine n pi ct over L is equal to 1. So that's what this term right here becomes 1. So this one becomes 1. And this term right here becomes 0. Sine of n pi ct, again, t is equal to 0 over L is equal to 0. So this term goes away. And so what you're left with is this Cn times 1 times this sine term. So you've got the Cn there times this sine term. Now our initial condition was that u at x comma 0 was equal to f at x. Now we see that if we plug in t equals 0 into u, into this expression here, we're going to just get Cn times this sine term. But this is equal to f. So what we see here is, oh, f has a sine series. So f is written as a Fourier sine series. So we know how to find the coefficients for that. Cn is equal to 2 over L times the integral from 0 to L f at x times sine of n pi x over L dx. So we can get Cn, we can find the Cn's by picking off the coefficients for the Fourier sine series for f. That identifies Cn, but what about Dn? How do we figure out what Dn is? So in order to use the condition on u sub t, the partial derivative, the initial velocity, we actually have to make an additional assumption, which is that we're assuming we can differentiate term by term. And if we do that, then we can use our initial condition to identify the dn. So our initial displacement tells us the cn's, and our initial velocity is going to tell us the dn's. So we assume that we're allowed to differentiate term by term. So then we have u sub t is equal to, so we just differentiate it. So this cosine becomes minus sine, and then you get these extra constants out here, the n pi c over L. And then we differentiate sine and we get cosine n pi c t over L, and by the chain rule you also get these constants n pi c over L. Now this has no t's in it, so we just leave this sine term alone. So if we assume that u sub t at x comma 0 is equal to g at t, again we plug in t equals 0. So what happens if you plug in t equals 0? So if t is equal to 0, then there you have t equals 0. So that means this is equal to 0. So all of that stuff goes away. All of the cn terms go away. And if t is equal to 0, then cosine of 0 is equal to 1. So then what do you have? You have that u sub t at x comma 0 is the sum, n equals 1 to infinity, of this dn term times n pi c over L times 1 times this sine term. So we don't want to forget this sine term here is this sine term here. Notice it just depends on x. So it's dn times, so this dn is that dn, and n pi c over L is that n pi c over L. And we also have the cosine term, but this cosine term is 1. So it's 1. So you're multiplying by 1, but you don't see that. And that equals g at x, this sum. So if that equals g at x, what can we say? Well, we see now that g is the sum n equals 1 to infinity of some constants times sine of n pi x over L. So g is actually a sine series as well. So in order to pick off the coefficients, we say that the coefficients, which are given here, are equal to 2 over L times the integral from 0 to L of g at x times sine n pi x over L. So this integral times 2 over L gives us the coefficients, but the coefficients are right here. The coefficients are right there. So we have n pi c over L, and we also have the dn, which is right here. So in other words, to solve for dn, you multiply both sides by L over n pi c. Now the L's will cancel. This L cancels with that L, and then you'll just end up with 2 over n pi c times this integral from 0 to L of g at x times sine of n pi x over L dx. So therefore, a solution to the initial boundary value problem is given by u at x comma t is the sum of these cn's times the cosine terms plus dn times the sine terms. All of that is a function of t times sine of n pi x over L. But we actually know how to compute these c's and d's. So c is the Fourier coefficient of f, and the dn terms are a multiple of the Fourier coefficient of g. So it's just L over n pi c times the coefficient of g, the Fourier coefficient of g. So we actually have formulas now that allow us to compute them. So let's look at an example. Here we have an initial boundary value problem where we're looking at the wave equation u sub tt equals alpha squared u sub xx, where we're not specifying a value for alpha. We are specifying a length of our string, so L is equal to 2 in this case. L equals 2. 2. That's close enough to a 2. So in this case, we're going to start with our boundary conditions being 0. So u at 0 comma t is 0 for all t, and u at 2 comma t is 0 for all t. So that means we're imagining a string, and you can see the sketch on the right of our function. So this is the initial situation. So the initial condition here is that u at x comma 0 is x when x is between 0 and 1, and it's 2 minus x between 1 and 2. So this is the graph of that. So the initial setup, you can imagine, is that we've fixed the endpoints at 0, and we're pulling up the middle and holding it here at height 1. But we're not imparting any initial velocity. So we're just letting go of it, and then we're going to see how the string vibrates. So that's the setup. So in this case, since u sub t at x comma 0 is equal to 0 for all x, we don't have to worry about computing the dn coefficients, the d sub n coefficients. Those are all going to be 0. So if we just look at our formulas, the dn coefficients are the coefficients for g. Well, they're the constant multiple of the Fourier coefficients of g, the Fourier sine coefficients. So those are all going to be 0. So dn is going to be 0 for all n. Now to find Cn, we can compute directly using this formula for the Cn's. So Cn is equal to 2 over L times the integral from 0 to L of f at x sine n pi x over L dx. But L is equal to 2. So 2 over 2 is just going to give you 1. And then we have the integral from 0 to 2. And then we have a 2 here, n pi x over 2. Now this function is piecewise defined, so on the interval from 0 to 1, f at x is equal to x. But on the interval from 1 to 2, f at x is equal to 2 minus x. So this gives us two integrals. You can integrate both of them using integration by parts. So for the first one, you let u be equal to x, and then dv is sine of n pi x over 2. And the same dv for the second integral, but now u is 2 minus x. So if you work that out, you should get something that looks like this. For the first one, u times v minus the integral of v du, and the interval here is from 0 to 1. That's why you don't want to combine this into one integral and just do integration by parts once, because this is on the interval from 0 to 1, and this is from the interval 1 to, or on the interval from 1 to 2. So here's the first one using integration by parts, and here's the second one. Now if you simplify all that, you get these expressions, and you get some cancellation here, and you just end up with this term and that term, which are the same, so they double up, so you have this. So your Cn coefficient is 8 over n squared pi squared times sine of n pi over 2. Now you can rewrite this if you want. Sine of n pi over 2 is either 0, 1, or minus 1, depending on what n is. If n is an even number, then this is sine of n pi over 2 is just going to be 0. If it's an odd number, then you're going to end up with either plus 1 or minus 1. So I've rewritten n, so if n is equal to 2k for some k in n, then you get 0. But if n is an odd number, so it's 2k minus 1, then you end up with this factor of minus 1 to the k plus 1. Either way, that gives you the coefficients. So you can just plug them in. So u at x comma t is given by this formula. The dn's are all 0, and the cn's are right here. These are the cn terms right there. So I just plug them in. You can rewrite it in terms of k if you want. There's really no need. You could just leave it in terms of n like this. That's more of a sort of a nicer form, but it has a lot of zeros in it. If you write it like this, it doesn't have any of those zero terms. And that's the solution to that wave problem. What happens if you have non-homogeneous boundary conditions? Well, the situation becomes much more complicated in that case in general. However, if you have a heat flow problem, for example, so this is a heat flow problem, and we're going to keep the boundary conditions constant, but we're going to allow them to be non-zero. So this is, in some sense, the simplest case where you have non-homogeneous boundary conditions, because they're constant. They don't depend on time. If you have more complicated boundary conditions, then that can lead to a much more sophisticated technique that you would need in order to solve the problem. So let's suppose, and even in this case, which is the simplest case, where you have a heat equation where the boundary terms are constant, you do need some sophisticated argumentation. And really, this is the idea. So we anticipate that as t goes to infinity, a steady state temperature distribution will be reached. Now, we anticipate that because we see that it's being held constant at one end and constant at the other end. So we imagine eventually that will lead to some sort of steady state temperature distribution. And you can easily determine what this is, the steady state distribution. Let's just call it V. Now it has to satisfy the same differential equation, because it's really U, it's just what U becomes over a sufficient amount of time. So u becomes this v function, which no longer depends on time because enough time has passed that we've achieved a steady state or equilibrium temperature distribution. But it has to still satisfy the heat equation. So that means the derivative with respect to t is equal to k times the second derivative with respect to x. Now I suppose these should really be partial derivatives here, but the partial derivative with respect to t is 0 because v doesn't depend on 0. So even though I probably should have written partial derivatives, it really is an ordinary derivative because v just depends on x. So that's the second derivative. So the k times the second derivative of v with respect to x is going to be 0. So that means that v prime prime is 0. So that means that v prime is constant and v is linear. So v at x is equal to ax plus b for some constants a and b, which you determine using the boundary conditions. So you can just show by direct computation that if v of 0 is equal to t1, then that means b has to be t1. So v of L is AL plus B equals T2, but B is equal to T1, so that means that you can just solve it for A as T2 minus T1 over L. So V of T, not V of T, rather V of X, V of X is temperature 2 minus temperature 1, T2 minus T1 times X over L plus T1. So this is our steady state temperature distribution. So what we're going to do is we're going to write U as W plus V, where V is the steady state term and W is changing over time, so you can call it a transient term. So W is the transient term and V is the steady state term. So if you can identify W, then you know what U is, because we know what V is. So U is W plus V. We know V, we want to find U, so that means we need to identify W. Now what we can say about W is that it satisfies a homogeneous differential equation, or that is to say, it satisfies the heat equation with homogeneous boundary conditions, because W is equal to U minus V. So we can set up the heat flow problem for W. So let's just do that. So W is U minus V. So if we compute the partial derivative of W with respect to t, that's the partial derivative of U with respect to t minus the partial derivative of V with respect to t. But of course V doesn't depend on t, so that derivative is 0. So we just end up with the partial derivative of U with respect to t, but U satisfies the heat equation. So that's equal to K times U sub xx. That is, the partial derivative of U with respect to t is equal to K times the second partial derivative of U with respect to x. That's just the heat equation that we started with. It's right here. It's this one right here. Okay, so we've computed the partial derivative of W with respect to t, and we see that it equals K times U sub xx. Now what about the partial derivative of W with respect to x twice? So that's going to be the second partial derivative with respect to x of U minus V, which is, of course, the partial derivative of U with respect to x twice, minus the second derivative of V with respect to x. But that's 0. Remember we already knew that V prime prime was equal to 0. So that means that this term is 0. So you just end up with U sub xx. So what does that tell us? W sub t is equal to K times W sub xx. So it's the heat equation. So W satisfies the heat equation. And if you check what it looks like on the boundary, W at 0 comma t is U at 0 comma t, but U at 0 comma t is T1, and so is V at 0. That's also T1. So these are 0. Now this isn't a surprise because remember, V is the steady state solution for U for this problem. So V is what U becomes in time. So the idea that, and we know that the endpoints are being held at a constant temperature. So whatever that constant temperature is for U, it's still going to be the same temperature for V. So U minus V at the endpoints is definitely going to give you 0. So you end up with the homogeneous heat equation problem, or the homogeneous heat problem. Now what about the initial condition? The initial condition is W at x comma 0,
t is equal to 0. That's what we mean by initial condition. So that's u at x comma 0, which is f, and v at x comma 0, but v doesn't depend on time, so that's just v. So that means we have the following homogeneous initial boundary value problem. W sub t is k times w sub xx. We have 0 at the boundary, and we have an initial condition. W at x comma 0 is f at x minus v at x. So this is a homogeneous problem, and we know the solution. W is equal to the sum, n equals 1 to infinity of bn times e to the minus k n squared pi squared times t divided by l squared times sine of n pi x over l, where the bn's are the coefficients for the sine Fourier series for the initial condition, which is f minus v, which is this thing right here. Now u is w plus v, and we already knew what v was. It was this linear term here. And now we also know what w is. W is this infinite sum where the bn's are given by that formula. So this gives us a solution for u, which is a solution to our original problem. And we obtain that by transforming the problem from one which is non-homogeneous into one that was homogeneous, because we already knew how to solve the homogeneous problem. So that allows us to solve the non-homogeneous case, at least when the boundary terms are constant, even if they're not 0.